So today we're going to review stuff that you're probably already familiar with, okay? And that would be, what constitutes an ionic compound, okay? Talk about kind of how they work, and then look at naming simple binary ionic compounds. And then hopefully before the end of class today, we'll move into naming ionic compounds that have what we call multivalent metals. Okay, that's probably something new that you haven't done before, okay? And if we're really moving along well, we'll get into ionic compounds containing polyatomic ions, okay? And that will also likely be new to you. The good news is that there's not a lot of really new stuff, and it's not terribly difficult either, it's just new. Okay. So we have to be able to identify a compound as either ionic or molecular, and then write the formulae and proper names for those chemical compounds. And I will get you guys periodic tables today. I think you have enough in there. Okay. All right. If something is ionic, what does it have in it?
A metal and a non-metal.
A metal and non-metal. So one thing from either side of the staircase. Okay, on the periodic table, everything to the left of the staircase is considered a metal, everything to the right of it is considered a non-metal, and an ionic compound contains one of each. Okay, or it contains a metal and a polyatomic ion, or a polyatomic ion and a non-metal. Okay, but we'll get to those in a bit. All right, now the thing about ionic compounds and ionic bonds, right, because we kind of have to understand how ionic bonds work. Okay? An ionic compound forms when a positively charged metal exchanges or donates an electron to a negatively charged non-metal. Okay? This exchange of electrons, okay, allows the metal and the non-metal to gain what would be considered an ideal electron configuration. Okay? So this is where, if you recall, we talked about Bohr's model that had the it was the kind of the planetary model where the electrons went around. Okay? This is kind of why we still accept it. It's used and it does a good job of explaining why ionic compounds occur in terms of why does a metal want to bond with a non-metal. Okay? And the answer is they both get something out of it. That's going to sound sociologically awful, but it's going to get worse. Okay? Don't try and make it sociological. It's science. Okay? It's chemistry. It's not about interpersonal relationships or the choices you make. Okay? Just putting that out. All right. So what happens, okay, in an ionic bond is, what is it doing that again for? Okay. So what happens when an ionic compound is formed is a metal gets a full outer ring or outer shell of electrons. Okay, so according to Bohr, and what's kind of true from a kind of simplistic point of view, okay, is if I had a sodium atom, okay, sodium has 11 protons and it has 11 electrons. Okay, and it has 12 neutrons. Okay. So, according to Bohr, the first ring of electrons can hold 2 electrons. Okay? And then there's more and more rings as we go, and each of the successive rings can hold 8 electrons. Okay? So a sodium atom has 3 rings. And its last ring has only 1 electron in it. Okay? All elements want to have their outer shell full. They can do that by doing one of 2 things. Finding a home for the electrons they have and dumping them. Or filling up their outer shell by taking them from someone else. Okay? Metals typically give away their electrons because their rings tend to be less than half full. So it's easier to give away those electrons than to try to find more to fill it. Okay? Non-metals are the opposite. Okay? Their shells are more than half full, and it's easier to pick up some electrons to fill them than to find homes for all the ones they already have. Okay? So for sodium, okay, the quickest way to fill its outer shell is to dump the single electron that's in that outer shell and then use the shell below it as the full shell, okay, rather than pick up 7 more. Chlorine makes a good pairing for sodium, okay, because chlorine has 17 electrons. So its first shell has 2, okay, the next shell has 8, and the next shell has 7, but it can hold 8. Okay, this is why they get along so well. Okay, sodium's got 1 electron it wants to get rid of, chlorine needs 1. Okay, so in an ionic bond, this electron is donated from sodium to chlorine. Okay, everybody with me so far? Now, once that happens, sodium has now more protons than electrons because it just gave away a negative charge. Right? So now sodium is an ion, and it is a positive 1 charge. Okay? Chlorine has just picked up an electron and now has a negative 1 charge. Okay? So ionic compounds are made of charged particles. Okay? Everyone okay with that so far? All right. Now, the thing about ionic bonds is they're very weak. And the reason for that is, this is the part that's going to sound awful sociologically. There's no reason for them to stay together anymore because they both got what they wanted. Okay? They both got what they wanted. Now they got their outer shell full, so what do I need you for anymore? Pretty good. Okay, it doesn't really work that way, but that's kind of what happens. Okay? So, ionic compounds can split very easily into charged particles. Okay? So, if I was to say pour salt into water, the salt dissolves very easily, and now that solution has positively charged sodium ions and negatively charged chlorine ions floating around inside. It's no longer sodium chloride. Okay? It dissociates and comes apart. Right? Which is why a solution of salt water can conduct electricity, but distilled water can't. Okay? There have to be these charged particles in there to allow the electrons to flow. All right, so what you really need to know is this. Metals give up electrons and become positive. Nonmetals gain electrons and become negative, and it's a weak bond. Okay? That's essentially what you need to know for science 10. Okay, questions on that? All right, so if I put sodium and chlorine together in an ionic compound, what would that compound be called?
Salt?
Okay, actual chemical name.
Sodium chloride.
Sodium chloride, yes, and the symbol would be NaCl. Yeah. Okay, now the reason we don't use salt as the name is because salt is actually a general term that describes any ionic compound. Because all ionic compounds are crystalline solids at room temperature, so they all look like crystals, like salt. Okay, so salt is actually a general term, even though we always apply it to table salt, which is sodium chloride. Okay, so we would be looking at then sodium chloride. We always name the metal first and the non-metal second, and we change the ending of the non-metal to I. And that's all there is to naming an ionic compound. Okay, right, the metal first, the non-metal second, change the non-metal to I. Right, so naming them is pretty straightforward. Do I ever have to put in prefixes? No. Okay, so if I had this stuff, any idea what that would be? Calcium chloride. Okay, not calcium dichloride because I don't use prefixes in an ionic compound. Why don't I? If I say calcium chloride, how will people know there's 2 chlorines?
Look at the charge on chloride.
Right. Right. The charges have to balance. It's why you do the drop and swap, or swap and drop, whichever way you were taught that. Okay? It's why you do the drop and swap when you're making the formulas, is the charges have to balance out. An ionic compound has to have an overall charge of 0. Okay? Calcium has a 2+ charge. Chlorine has a 1+ charge. Okay, so there needs to be 2 chlorines to bond to any single calcium atom. Everyone okay with that idea? Okay, so then what that means is I don't need a prefix because there's only one way that calcium and chlorine can go together and have the charges work out. Okay, that's why we don't use prefixes in ionic compounds. There's only one way calcium and chlorine can go together. Okay, there's only one way sodium and fluorine can go together. All right, there's only one way that magnesium and oxygen can go together. Okay, so we don't have to use prefixes in those compounds. Okay, all right. So remember, we name both ions, and this is something important because I see this one happen all the time. Names of compounds are not proper names. Okay, it's not like Jane Doe or John Smith. Okay, they're not a proper name. They're a chemical designation. Thus, they do not get capitalized. Okay, unless you're starting a sentence with sodium chloride tastes good on my French fries. Okay, then you would capitalize it because you're starting a sentence. Okay, but otherwise, no. Okay, they don't get capitalized. Okay, questions there? All right, I'm going to hand out the periodic tables because we've got to need those here. Okay, you're definitely not going to want to lose that. You're going to need it a lot. Okay? Common question right after I hand these out. Mr. Coderre, do I have to memorize this thing? Hell no. Okay? You do not have to memorize the periodic table. That would be silly, especially since it's part of the data booklet you would get on your Chem 30 diploma exam. Okay, why would I make you memorize it in grade 10 if they're just going to give you exactly that piece of paper, okay, on your Chem 30 diploma? Okay, so note you don't have to memorize it. Are there things on the periodic table that you will have to memorize? Sort of. Okay, there are some things on there that, well, some things that aren't necessarily on the periodic table, but that you would have to know how to do. Okay, and the reason is this. If you write all over your periodic table, you can't use it on your unit exam. I'll give you a fresh one without all your little jot notes on it. Okay, so be cautious as to how much you write on there. Okay, one of the things that people often write on there that they shouldn't are the charges of all of the materials. Okay, now, for most materials, okay, you'll see the charges are actually right in there. Okay, especially for the metals. Okay, so everything that's in group 1 is a +1 charge. Everything that's in group 2 is a +2 charge. Okay, everything in group 3 is a +3 charge. And then it starts to get a little bit crazy. Okay, then you'll see that there are some metals that have more than one possible charge. That's something we'll talk about later on today. Okay, what do we do in that case? It gets trickier when you get over here to the nonmetals. Okay, the nonmetals don't have charges listed. Okay, but they are in the same pattern as the metals are. Okay, everything in group 18 has no charge. These are the noble gases. Their outer shells are already full, so they don't have a charge. Okay, everything in group 17, which is one less than the full shell, is -1. Okay, so everything in this one is a -1. Everything in 16 is -2. Everything in 15, -3. Okay, and then we don't really deal with these ones. Okay, all right, so -1, -2, -3. Okay, those are the charges for those columns. Okay. All right, and something else that we'll learn about later on, okay, are gonna be the kind of special molecular elements. There are some elements that when they're by themselves end up in groups, okay? There's only a few of those to remember. It's pretty straightforward to remember those. Okay, here's what I would like you guys to try. Let's see how much you remember. I want you guys to try the first 6 here. Well, we already did number 1, so let's not worry about number 1. I want you to write the names for the first 6. Okay? And I would say probably write down the question. So number 2, go KF, and then write what KF is. Okay? All right, I'll give you a few minutes to get ahead of me on that, and then we'll walk through them together. Okay, remember, metal first, non-metal second, non-metal ends in I. Okay, so looking at number 2, what would I have for a name for KF?
Potassium fluoride.
Potassium fluoride. Okay, what about number 3?
Hydrogen monodide?
Hydrogen, would I use a prefix? Hydrogen,
It's a gas.
it's a gas, but it's a metal. Gas is its state, but it behaves in a metallic fashion. Okay, so even though it is a gas, we still consider it a metal. In the same way that mercury is a liquid, still a metal. Yeah?
So hydrogen iodide.
Hydrogen iodide, exactly. And that's a tricky one, because hydrogen can actually go both ways. Okay? It can behave as a metal, which is what it usually does. Okay? Especially if it's in an ionic compound, it's going to act as a metal. Okay? But in some molecular compounds, especially organic molecules, okay, it can behave as a nonmetal. Right? It can get an outer shell one of 2 ways. It can gain an electron and fill that first shell, or it can lose an electron and have no shell. Okay? Either way, the problem is solved for hydrogen, okay? Which is why it behaves most of the time as a metal, okay? But it can also behave as a non-metal. Okay? How do you tell the difference? Is that what you're going to ask?
No.
Oh, okay. What were you going to ask?
I was gonna say good to know.
Good to know. Okay, it is good to know. But here's how you can tell if it's behaving as a metal or a non-metal. If it's listed first, it's behaving as a metal, because we always list metals first. If it's listed second, or anything else other than first, it's behaving as a non-metal. All right, so if I was looking at this, for example, okay, that's butane. It's the stuff that's in lighters. Okay, in that compound, hydrogen is behaving as a non-metal. It's not listed first.
So if it was second in an ionic compound, that would never happen, right?
No, it could. It's pretty rare. I don't think I would have a situation where I would make one like that. But if it was listed second, then it would be like magnesium hydride. Right? I would just treat it like any other non-metal and change its ending to I. It's not really something that I think you're going to have to worry about. Okay. All right, so this would be hydrogen iodide. Okay, what about this stuff? CaBr2.
Calcium bromide.
Calcium bromide. Okay, number 5.
Aluminum acetonitide.
That's a tricky one, right?
Acetite?
Astatide. Yeah.
Acetatide.
Astatide. So
Added too many N's and T's into there.
yeah, it's one of those tricky ones. There's a few like selenium, where it can be selenide or selenamide, and either one is okay. Oh, see, and then I went and did too many syllables on aluminum. Alum.
Aluminium.
Don't say it like that. I don't write it or say it that way. I'm stubborn. Okay. Actually, I think it actually like sounds all prim and proper, especially when an English person says it. Aluminium. It's just I don't know what it is about. But then I say it myself, and it doesn't sound good. So I always say it aluminum because I drive an all aluminum truck, not an all aluminium truck. It just doesn't sound right when I say it. I love how it sounds when a person with an accent says it, especially an English accent. It just sounds so nice and prim and proper, but it just doesn't sound right out of me. Okay, pass the tide. All right, and I will accept either one. If you write aluminium, if you write it that way, that's totally fine because it's also correct. Okay, what about number 6? Cesium sulfide. What did I not do with any of my names? No capitals. Have a look at yours. See how many times you may or may not have capitalized. Since you have it, you'll have to break. Okay? I'm not going to mark them wrong if you do capitalize them, but just know they're not supposed to be. All right. Is this ringing a bell? Feeling familiar? Okay. Okay, try the rest of them. All right, we'll quickly go through the rest here, guys. So number 7 would be sodium oxide. All right, no prefixes. All right, number 8, Ba is barium, Se is selenium. This can be barium selenamide or barium selenide. I write selenide because it's shorter and I don't have to write as much. So selenide is fine, selenamide is also fine. Okay. Number 9, Ra is radium. And then it's telluride. Okay, which is the way to write the ion, not the name of the car. Kia makes an SUV called a Telluride. I'm like, that's weird. What a strange name for a car. All right, number 10. Okay, we got Li, which is lithium fluoride. Okay, and then number 11, Rb is rubidium sulfide. Sulfide, yeah. In that one it's sulfide, not sulfuride. Okay, we take that UR off of that one. Okay, number 12, Sr is strontium. And then iodide. Strontium, iodide. Strontium.
It doesn't say that.
Does it say strontium on there? Did they change that one too? They did. Okay, so we could say strontium iodide as well. That must be another one they changed with aluminium. It sounds awful when I say it. It feels awful. It's like nails on a chalkboard. Okay, number 13, we have calcium oxide. Okay, and then we have magnesium selenide. Or selenamide, either one. Okay, questions on any of those? Okay. Then, we got to talk about what happens with our multivalent metals. So if you're looking at your periodic table, basically between group 4, okay, and like group 13, 14, 15 even, okay, the metals do some weird stuff. Okay, and most of those metals have more than one possible charge listed. Okay, now initially most people go and they look at that and they're like, so what's the problem? Here's the problem. Okay, the problem is this. What's that stuff called? Iron oxide. Okay, what's this stuff called? Iron oxide. Are they the same thing? That's a problem. Those are two very different chemicals. Okay, they have different physical and chemical properties. All right, I mean, it could be as bad as this. It isn't, but it could be. Okay, it could be that one of those is like rust and fairly harmless, and the other one is poisonous. And if I'm writing a paper about the health benefits of, chewing on a rusty nail for hemoglobin levels, and I write in that it's great to get iron oxide in your blood, and someone eats the wrong one and dies, I'm kind of at fault for that. So they probably shouldn't have the same name. Agreed? It was like the time when I had 2 Chase William Andersons in my class at the same time. And those 2 young men could not have been more different. Okay? But they had the same name. I sure hope I didn't screw up their marks. Because that could happen. They had exactly the same name. They had to put 1 and 2. Okay, beside the names when
Who
we
was
had
one?
stuff in.
Base off the-
Which what?
Which one was one?
The one that sat here, and 2 was the one that sat over there. You can imagine which one sat here. That's, like I said, they were very different. They could not have been more different. Okay, so yeah, we got to make sure that we have a way to tell these 2 things apart. So what we do is we put in their name a Roman numeral that tells us which charge the iron has in that particular compound. All right, now that means I got to be able to figure out which charge it has in that particular compound. Okay, here's where knowledge of ionic compounds becomes important. Okay? The most important thing about ionic compounds is the charges have to balance. That means there has to be the same number of negative charges and positive charges in an ionic compound. Okay? So that the overall charge is 0. Knowing that, I can always figure out what charge each thing has. Okay? Oxygen, always has a charge, according to our periodic table, of -2, because it's in group 16. Okay, and everything in that group that's a non-metal is -2. Iron can be +2 or +3. In this compound, which one is in there? A +2. It has to be, because that's the only way that compound ends up with a charge of?
Balanced.
0, yeah. Overall charge of 0, I have the charges balanced. Okay? So that's all I do, is I go, all right, so if this one's a -2, this one must be a +2. All right? In this compound, though, I got to do something similar. Oxygen's always a -2. But how many oxygens do I have?
3.
So how many negative charges in total are there?
6.
Right. Okay? So I've got 6 negative charges. That means I've got to get 6 positive charges out of my iron. Agreed? Okay. So I've got 6 positives, and I got to get it from 2 irons. What's the charge on each iron? 3. Is that very difficult math?
Oh, no.
Okay. So that's how I figure out. So this stuff is iron Roman numeral 2 oxide. Okay? This stuff is iron Roman numeral 3 oxide. Okay? Everybody all right with that?
What is iron Roman numeral 3 oxide? Is it like an actual thing?
Oh yeah, it's an actual compound. I can tell you what its properties are or whatever. I don't know, but yeah. They're both compounds. Now, when you see on your periodic table here, okay, and you see the charges listed, they are listed in the order of their commonality. Okay, and what that means is iron 3+ is far more common than iron 2+. Okay, like it's usually significantly more. Like one is like 80 to 90% of all iron, and the other one is a much smaller percentage. Okay, everyone all right with that? Okay. So does that mean you should know your Roman numerals?
Yeah, probably.
Yes, you should. Okay, so if you like sequels, okay, in movies, they usually use Roman numerals in those. All right, so we will have a list of Roman numerals here for you. when we get to 8, that one will remain nameless. It is the movie that will not be named. Just so you know, 'cause it's awful. Okay, so 1, 2, 3, okay, we got A New Hope, and then the greatest movie ever made, The Empire Strikes Back. If you disagree, you're wrong. Okay, and then we have, whoop. Then we have, okay, Return of the Jedi, Force Awakens, then we have the movie that shall not be named, and then we have The Rise of Skywalker, which wasn't awful, but wasn't very good. Okay?
Skywalker.
Hmm?
Not even Skywalker. Never mind.
Okay, so that's what they look like up to 9. We're probably not gonna have to go past that. In fact, you rarely have to go past 4. Okay, so as long as you know like 1 through 4 pretty well. Okay, so this is one of the things that's kind of on the periodic table, but not really on the periodic table, but it's something you need to know. You need to know your Roman numerals. Okay? They get crazier obviously as you go up. Watch Super Bowls. Okay? It's like this whole long list of Roman numerals before the name of the Super Bowl. Okay? All right. Everybody okay with that? All right, so I'm gonna put a few up there, and I'm gonna see how you guys do with writing the name. So you gotta put in a Roman numeral, okay? And remember, the way we figure out which Roman numeral it is we simply use the non-metal. There are no non-metals with more than 1 charge, so we can always use them to get started. Okay, we write the charge on the non-metal, figure out how many negative charges there are, put that number over on the metal to figure out what charge the metal must have.
Sorry, I missed what the charges were for boron, carbon, and silicon.
You won't have to worry about those. They can be, boron is often a plus, okay? Carbon and silicon are usually plus or minus 4 because they're exactly halfway in the middle, right? So they can be either way. All right, so we just did number 1. So let's have you guys try 2, 3, and 4. Okay, give you a few minutes on 2, 3, and 4, and then we'll walk through those. All right, so on our first one here, we've got cobalt with sulfur. Okay, sulfur is always a -2 charge, and cobalt can be a 2 or a 3, right? Yeah. Okay, so if cobalt is a -2, or sorry, if sulfur is a -2, and there's only 1 sulfur here, okay, and there's only 1 cobalt, the cobalt must have a charge of +2. It's got to have the same charge then. If they're 1 to 1, they have to have the same charge, right? So this stuff then would be cobalt, Roman numeral 2, sulfide. Okay, everybody all right with that? Good. All right, for our next one here, so we've got manganese, okay, and manganese can be a 2 or a 4, okay, and it's with chlorine. Chlorine is always -1. Okay, so if there's 4 chlorines, each one having a -1 charge, how many negatives are there? 4. Okay, so I've got 4 negative charges. That means I've got to get 4 positive charges out of my single manganese, so its charge is 4. Okay, and we just write manganese, Roman numeral 4, chloride. Okay, now here's the danger that comes along with this. When do I need to use a Roman numeral? With the transition metals, or any time the metal I have in the compound has more than 1 possible charge. I don't need to use a Roman numeral for calcium, or magnesium, or lithium, because they only have 1 possible charge. Okay? The only time I use a Roman numeral is if on the periodic table there's more than 1 charge beside it. Okay? So I just don't want you to over-apply it. Okay? That happens just as often, if not more often, than completely forgetting to do it at all. Okay? people just start putting Roman numerals on everything because they think they need to. You don't need to. You only need to use it if you're dealing with a transition metal. Okay? All right, for number 4, we got copper with sulfur. Copper can be a +1 or a +2. Okay? Since it's with sulfur that has a -2 charge, this must be copper 2. Okay? Questions on those so far? All right. Let me try 4 more. Okay? Actually, just 3 more. We won't do number 8. Okay? Let's do 3 more, and we'll have time to do those and get through them together, and then we'll call it. All right, so looking at the last 3 here, okay, so we're going to have tin, and it's with tellurium. Tellurium is always a -2 charge, which means I have 4 negative charges. The possible charges for tin are +2 and +4. This is tin 4. Telluride. All right. Hg is mercury, okay, and it is with astatine, okay. Astatine's always a -1, okay, so that means there's 2 negative charges. Mercury can be a +1 or a +2, so this is mercury 2 astatine. Okay, and our last one here, polonium, is with iodine, okay. Iodine's always a -1, so that means there's 4 negative charges. Since there's only 1 polonium there, its charge must be +4. So this is polonium 4, iodine. Okay, so tomorrow we'll pick up where we left off, and we'll get into naming polyatomic ions tomorrow as well. Okay, remember Friday has shortened classes, all right? So you won't have as big a breaks in between, and you don't have lunch tomorrow. As well, school is done by lunchtime, okay? So 12:20, we're done the day tomorrow, okay? Was it worth your while to do the practice quiz?
Yes.
Okay. It'll always be worth your while to do the practice quiz. It won't always be exactly the same, but it'll always be worth your while.
I still can't get it.